Welcome to part 2 of reaction rates, and in this case we are going on with the factors affecting reaction rates. In part 1 we covered concentration and temperature. Now in this part we are going to continue with other factors affecting reaction rates. The third one in this case is surface area. Now, when we talk of surface area, then we are looking at the size of the reacting particles. Let's say in a setup where we have, setup A, where we are reacting calcium carbonate, but they are unground. Normally referred to as marble chips, unground calcium carbonate reacting with 1 molar HCl, which is of course 40 cubic centimeters. Let's say this one we are using 5 grams, and then we have in setup B we have 40 cubic centimeters of HCl, 1 molar. Then here we are adding also calcium carbonate, which is powder. It's powdery. In this case, setup A, if we react unground calcium carbonate with HCl, then of course we expect the formation of calcium chloride plus let's say we have calcium chloride plus water plus CO2, that is carbon dioxide. So unground marble is normally having large particles and in this case we consider this one to be having smaller surface area. The reason why it is having smaller surface area is because the area of contact between these large particles and the ions of hydrochloric acid is very small. But when it is ground, that is the powdery, it is considered to be having larger surface area. So during the reaction, you'll realize that when you put the unground marble, that is calcium carbonate, into this acid, that is 1 molar hydrochloric acid, 40 cubic centimeters, then you expect effervescence, that is formation, evolution of carbon 4 oxide. Now, this reaction will take longer time, and the rate at which carbon 4 oxide gas will be evolved will be very low, or we say slower rate, because of smaller surface area. So you expect this reaction to take longer time. Let's say that the time it will take for the marble chips to be consumed, let's say, is 100 seconds. Then in this case, it will take shorter time for the reaction to come to an end. Now this is because by grinding the marble chips into powder or using the powdery calcium carbonate, it increases the surface area of contact between the calcium carbonate and the ions of hydrochloric acid. That one will mean that the frequency of collision will be high because of the many particles smaller in size. So we term it as larger surface area. So if you are to illustrate this one graphically, that is in terms of volume of carbon 4 oxide produced per unit time in seconds, then you'll realize that if this one is for powdery calcium carbonate, then this one will be for unground. The graph for powdery calcium carbonate is steeper compared to the graph of unground calcium carbonate. Now, one thing you have to notice that though we have the same volume, I mean the same concentration of hydrochloric acid, and then we also have the same quantity of calcium carbonate used, their surface areas is actually the variable. And so in terms of the volume of carbon 4 oxide evolved, it will be the same. Reason being, we used the same quantity of the reactants. But the rate is what will vary. That is the frequency at which carbon 4 oxide gas is evolved. So that one will be the factor that will determine the steepness of the calcium carbonate. That is the volume of carbon 4 oxide evolved per unit time, that is per second, denoted by cubic centimeters per second. This is an area that is commonly tested in exam, especially theory, chemistry theory. So you have to note how to interpret graphical illustration of surface area. Then the next factor is catalyst. How does catalyst affect the rate of reaction? In Form 1, you must have learnt about the preparation of oxygen gas by decomposing hydrogen peroxide using manganese 4 oxide. To form water and oxygen gas. Now, you must have learnt in Form 1 that a catalyst is any chemical substance which speeds up the rate of a chemical reaction but is not altered. That is, it doesn't change in terms of the quantity. When looking at a catalyst as a factor, we can consider two setups still. Setup A, where we have, let's say, 40 cubic centimeters of hydrogen peroxide. And then we have setup B, or still 40 cubic centimeters of hydrogen peroxide. Now setup A is without catalyst, and then setup B with catalyst. Now if you just leave hydrogen peroxide on a bench, that is 40 cubic centimeters of hydrogen peroxide in a bench, then you will realize that hydrogen peroxide decomposes at a very slower rate. That is without a catalyst. It decomposes at a very slower rate. And that is why naturally you will see very tiny bubbles. And those ones are of oxygen gas produced during the process of decomposition at a very slower rate. However, in setup B, if you add just, let's say, 2 grams of manganese 4 oxide, which is a black powder, you'll realize that it takes very short time for decomposition to take place. And this one is observed by production of rapid effervescence of oxygen gas. So you will see so many bubbles within. Rapid effervescence, that is oxygen gas being produced at a faster rate. And that is because manganese 4 oxide that has been added here speeds up the rate of decomposition of hydrogen peroxide to form water and oxygen gas. Now in this case, the question is this: how does catalyst cause reaction rate to increase? The bottom line information is that catalysts lower the activation energy. Catalyst speed up the rate of a reaction by lowering the activation energy of the reactants. So that is the reason you can give. If you are told to explain why or how does catalyst increase the rate of reaction, then you say they increase the rate of reaction by lowering the kinetic energy. And that is the minimum energy, the activation energy, which is the minimum energy required to cause successful collisions of the reacting particles. This one can be illustrated graphically. And in this case, we are comparing two setups. So this is energy in kilojoules, and then this is reaction path. So suppose here we have hydrogen peroxide, then this is water and oxygen gas. Now this one is for catalyzed reaction, and then this is for uncatalyzed. So we have actually plotted two graphs for the two sets of reaction. Now the energy barrier that has to be overcome for the uncatalyzed reaction, that is where we have the hydrogen peroxide is allowed to naturally decompose, the energy barrier is steeper. And this one means the activation energy required is higher. Now when the catalyst is added in this setup B, the activation energy is lowered. And so you expect rapid evolution of oxygen gas. So this one is a graphical illustration of how catalysts affect the rate of reaction. Now the next factor is pressure. Now, one thing you must have known about matter is that matter exists in three states, that is solid, liquid, and gas. Now, pressure as a factor does not affect the reactions which involve solids or liquids. This is because solids and liquids are incompressible. They cannot be compressed. So that is why pressure does not affect reaction rates where solids or liquids are involved. That is, the reactants. Now, reactions involving gases are normally affected by pressure. This is because gases are compressible. The question is this: how does pressure affect reaction rates involving gases? Let's say a case whereby ammonia gas is reacting with hydrogen chloride gas to form ammonium chloride. How does pressure affect the rate of reaction? The answer is increase in pressure increases the rate of reaction involving gases. What pressure does is that pressure makes the reacting particles to be squeezed, to be closer together. And so, because of that, the frequency of collision of the reacting particles increases. That is what causes increased rate of reaction, leading to formation of products. So that is how pressure affects the reaction rate. Now the next one is light. Or we say light energy. Now in this regard, we are focusing on UV light, ultraviolet light, that is light from the sun. Now the first point is that light is a source of energy. And there are some reactions which require light energy to take place, while some do not require light energy. Now, let's take a case where a case of photosynthesis. In photosynthesis, carbon 4 oxide combines with water to form carbohydrates. Carbohydrates plus oxygen gas. So we need light energy. Now, without light energy, plants cannot manufacture food. They actually need light. And the role of light is to cause the splitting of water molecules so that the hydrogen atoms can combine with carbon dioxide to form carbohydrate. Without light, there is no photosynthesis. Now, with your knowledge in biology, increase in light intensity increases the rate of reaction. And that is because it increases the rate of photolysis, or breakdown of oxygen, of water into hydrogen atoms or hydrogen ions, and oxygen gas. So if you are told to explain how light affects the rate of photosynthesis in chemistry, then you simply say that light increases the rate of photolysis or photolysis or breakdown of hydrogen atoms and oxygen gas. thereby causing the hydrogen atoms to combine with carbon dioxide to form carbohydrate. Another area is halogenation process. And in halogenation process, we normally have halogens combining with, let's say, alkanes. Let me use an example of methane. This is methane. Methane is written like this. Methane reacting with chlorine gas to form chloromethane and hydrogen fluoride gas. This reaction requires UV light. Without light energy, chlorine cannot combine with methane. And so that reaction only depends on light. So the rate at which halogenation process will occur, that is, or we say chlorination in this case, depends on the light intensity. If the intensity increases, then we expect increased chlorination process. In this case, the role of light is to provide kinetic energy, which is required to cause these molecules to collide and combine to form product. Then number two, the role of light here is to cause bond breaking. That is, if we have the structure of methane is like this, and then for chlorine is like this. So the role of UV light is to break the bonds, the covalent bond between the carbon and hydrogen, and then the same energy is also required for bond formation. So you can talk of energy in this process. Light energy in this process is required for bond breaking and bond formation. Then number two, light energy provides kinetic energy required for these molecules, these atoms, that is the hydrogen atoms, chlorine atoms, to collide so that they can combine to form products.
This is a city on a hill, a school with God's glory. Education is light, my Kadzonzo the only bright, shining star in the nation. Highly favored, my Kadzonzo, highly favored by God, so we are.